Hi class, welcome to our first video lesson on Chapter 2, 2-1, Inductive Reasoning and Conjecture. Let's first define both of those two terms. Here's what a conjecture is. Simply, it's just an educated guess. It's looking at a problem and making an educated guess about the conclusion of that problem. Inductive reasoning, making a conjecture based on examples. So what we're going to be doing here in this video lesson is we're going to be using inductive reasoning. We're going to be looking at some examples, and then we're going to make a conjecture, which is an educated guess. So here's our first one. Let's use some inductive reasoning. Make a conjecture about the next number of dots. There are two ways to approach this problem. Let's first think about it geometrically. So what some students want to do on this one, which is just fine, is they want to draw another picture about the next sequence here. So in our first diagram, we have one dot, and then it looks like we have two dots on the bottom row, and then one dot in the top, and then 3, 2, 1, and then 4, 3, 2, 1. That makes sense. So maybe we should think about having 5 dots on the bottom row, and then 4, and then 3, 2, 1. That would be some good inductive reasoning, wouldn't it? And so we would then make a conjecture. I bet there is going to be 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I bet there's going to be 15 dots in the next picture. So that is my conjecture. I made a conjecture about the next number of dots. So that's a geometric way of thinking about it. We could also think about it algebraically. So if I have one dot in the first picture, and then I have 3, and then I have 6, and then I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm given this information, and now based on the next, using my inductive reasoning, what would I anticipate this picture being if I didn't have that picture there? I could say, well, to go from the first picture to the second picture, I had to add 2. To go from the second to the third, I had to add 3. To go from the third picture to the fourth picture, I had to add 4. So what would be a possible conjecture I would make about going to the next picture? I would have to add 5. So what is 10 plus 5? 15. So there are two possible ways that you can make a conjecture using inductive reasoning. Let's now take a look at this one. 1, 1/4, 1/9, 1/16, 1/25. What conjecture would you make about the next number? Why don't you guys pause the video and see if you can get this one on your own. After you try this one on your own, maybe you got 1/36. That is the answer for this one. That is the conjecture that I hope that you reached. And what you kind of look at this one as, if you want to look at it this way, 1 is going to be in the numerator because that's been the pattern throughout. 1 is in the numerator, 1 is in the numerator, so on and so forth. What also you could look at here now for the denominator is that this number here is 1 over 1 squared. And then we have 1 over 2 squared. That's 1/4, right? 1 over 3 squared is 1/9. 1 over 4 squared is a 16th. 1 over 5 squared is a 25th. So our next number in the sequence, using our inductive reasoning, should be 1 over 6 squared. And there you get the number 1/36. Another way you could look at this is, again, by kind of saying to get from 4 to 9, you have to add 5. To get from 9 to 16, you have to add 7. To go from 16 to 25, you have to add 9. So wouldn't it make sense that in the next number, to go from 25 to 36, you would have to add 11, which indeed you do. 25 plus 11 is 36. So there's the next number in the sequence. It is 1/36. Let's make a conjecture on this one. For points L, M, and N, segment LM is 20, segment MN is 6, and segment LN is 14. Make a conjecture and draw a figure to illustrate your conjecture. Well, if I were to look at this one, LM is 20 units. So I can maybe draw a picture. LM is 20 units. And then mn is 6 and ln is 14. So if I just kind of look at the nature of these numbers, 6 and 14, if you add those two segments up, you would get 20. So if I had n being maybe somewhere right here, where now n to m, this blue segment, is 6. And then L to N is 14. So right here would be 14. So now I could say 6 plus 14 is 20. So that would all make sense, right? LM is the full segment, MN is a part of the segment, LN is the other part of the segment. When you add those two up, you get 20. So the conjecture that I can make is that L, N, and M, those 3 points, are collinear. That's a very logical conjecture, isn't it? Maybe you reached that one on your own as well. Some maybe thought something that looks like this. Maybe they saw, well, if LM is 20, if LM is 20, and then MN is 6, and MN is 6, maybe we have MN right here as being 6, and then LN is 14. So this is a whole different conjecture here. I'll draw a little line here so that it's something different. This may have been a conjecture that someone would make, and that's very good thinking. We have 3 segments. Maybe we're looking at a triangle here where LM is 20, MN is 6, LN is 14. We're still going according to the information that we're given, and we just made a different conjecture. So we might say L, M, and N make a triangle. Very possible conjecture. We'll actually find this out in a few chapters that this is actually impossible. We can't have segments with 6 and 14 and 20 and make a triangle. You'll learn that a little bit later. But that's very good thinking if you did think of something like that. So it's just using the information, using inductive reasoning, making a conjecture. A counterexample. A counterexample is an example that proves a statement false. An example that proves a statement false. If a statement is either true or false, or statements are either true or false, it only takes one counterexample to prove a whole statement false. Unless a statement can be proven true in every single instance, it's false if it can be proven false in just one instance. So if we have something like this on a graph or a chart, maybe you read this on a website or read it in a newspaper, something like that, based on the table below showing unemployment rates for various cities in Kansas, find a counterexample for the following statement. You sometimes hear about these kind of things, reading through different sources. The unemployment rate is highest in the cities with the most people. So unemployment rate is the highest in the cities with the most people. Well, if I look at this, Shawnee right here has the most people. So according to this statement, it should have the highest unemployment rate. Is 3.1 the highest unemployment rate? I would say the answer is no. My counterexample might be to say Osage right here. Osage is clearly not the largest city, 10,182 people, yet it has an unemployment rate of 4%. So my counterexample to this statement right here, unemployment rate is highest with the cities with the most people, would be Osage, because that clearly has the highest unemployment rate for not the highest city. So a counterexample is a statement that proves a statement false. So here's a question I have for you. Is Mr. Berge's conjecture true or is it false? If it is false, prove it is false with a counterexample. And a counterexample can sometimes be words, but oftentimes it could just be a picture. So picture or words. You could write to use a counterexample. So given line segment DE is congruent to segment EF, here's my conjecture. E is the midpoint of DF. So we have line segment DE. So I might maybe start to draw this. DE is congruent to segment EF. So here's E and F. So if DE has to be congruent to EF, then the conjecture I'm making is E is the midpoint of DF. So according to the picture that I just drew right here, this would be true. E is the midpoint of DF. Is there any way that I can draw a picture with this given information that proves this conjecture false? So is there a counterexample? Well, let's see if I could still, again, use this given information. Segment DE, so here's D, here's E. Let's make it congruent to segment EF. EF. Congruent, congruent. I just proved this conjecture false. Because in order for it to be the midpoint, they all have to be collinear. And D, E, and F in my counterexample are not collinear. D and E are on one line, E and F are on a separate line. So I just use a counterexample to prove my conjecture false. That's what a counterexample is. Let's practice this one more time. Is Mr. Berge's conjecture true or is it false? If it is false, let's prove it is false with a counterexample. So we're given 4 points, W, X, Y, and Z. With those 4 points, I'm going to make the conjecture W, X, Y, and Z are non-collinear. And I would say they're non-collinear in most cases. I might have W right here, X right here, Y right here, Z right here. W, X, Y, Z. And those 4 points would be non-collinear. So that would make this statement, the conjecture, true. Is there any way, though, that we can prove it false using a counterexample? Why don't you guys pause the video and try to draw a counterexample that proves this false? Well, hopefully you just drew one single line and you put all 4 points on the line. Here's W, here's X, here's Y, and here's Z. You just drew a picture that acted as a counterexample. W, X, Y, and Z are non-collinear. That is false. You just proved it by making W, X, Y, and Z collinear. So that is a counterexample that proved this false. Let me know if you have any questions on inductive reasoning and conjecture when you get to class tomorrow.